Yeah, thank you very much for your introduction, Murat. I hope you can hear me all. Yes, perfect. My name is Markus Gödker. As Murat said already, I'm a research associate at the group Engineering Psychology and Cognitive Ergonomics of Thomas Franke. And also, as Murat said, I'm particularly interested in the comprehension and use of energy in the context of human-machine interaction. So, especially in electric mobility, not human energy in the first place. But today, I'm very happy to present you maybe a novel approach to look at how we use energy to move ourselves around. So maybe this is a link of these two energy perspectives. And this will be my main issue actually. Furthermore, we launched one very first pilot study to give this novel perspective an empirical try. So that I will present also. And yeah, let's start at the very beginning. How do we move? So basically, this is what we do. Um, while walking, we use our muscles and therefore muscular energy to overcome distance in a certain time. And of course, for humans, this is not enough. In order to amplify those human capabilities of locomotion, humans have developed various mobility tools. Um, some of these vehicle tools achieve higher mechanical efficiency by using and controlling radial motion, like bicycles and all sort of vehicles using wheels, or they achieve higher mechanical efficiency because they're operated on water, like a rowing boat, for example. And again, other vehicles make use of external forms of energy, like wind in a sailing boat or fuel in electric cars. And in fact, all of them reduce the invested muscular energy for us humans to overcome the distance in the certain time. Um, but there's also a downside to this because controlling those tools increase the demands on cognitive human energy resources because we have to control the higher velocities or we have to make energy management of scarce resources, for example, in the electric vehicle. And of course, not only the demand for cognitive energy is higher, but also the demand for external energy, like fuel or electricity. So the demands on different types of energy are various among those vehicles. For example, when we look at the three types of energy and when we look at different forms of locomotion, like in this case, walking, riding a bike, riding an e-scooter, these e-scooters that you see nowadays a lot in inner cities, or taking an electric bus or driving an electric car. As I said, the demands on the different types of energy differ. So of course, when we look at walking, where almost no external energy, the only external energy here is maybe tailwind is used. So muscular energy limits this form of locomotion ultimately and must be used efficiently and controlled. A bicycle, for example, is a vehicular tool that achieves higher mechanical efficiency by using wheels. Therefore, the expended muscular energy and even the scarce external energy as tailwinds result in greater speeds and higher dynamics. So this in turn means that cognitive demands increase, and besides the primary muscular energy, cognitive energy gains importance. Um, and with the use of greater amounts of external energy, for example, in the electric car, the connection between muscular energy and the covered distance dissolves almost completely, and muscular energy becomes irrelevant. Furthermore, the use of external energy in the field of electromobility is even more complex. So you cannot recharge it easily and fast. So an empty battery means that the trip must be interrupted for a longer time, and this makes external energy a limiting factor. And so this energy management to plan the trip and to plan the charge also raises the cognitive load and consequently demands cognitive energy. So the point is, in this slide, whenever a type of energy is relevant, technical systems actually should be designed to optimally support an adequate understanding of these different energy demands and energy flows that are used for to overcome distance in a certain time. Of course, I'm aware that human physical energy is not exactly the same as external energy resources. So to be aware of these different maybe existing models of energy, of human energy that you also presented today, must be considered, like, for example, the Quinn model. And I mean, the main difference here is that for muscular energy and cognitive energy that are encompassed here in physical energy. So the presence and absence alone of these energy forms that may be present as glucose, adenosine triphosphate. This does not automatically lead to an energization or exhaustion. We need the energetic activation here. This may not apply for other resources and external energy. But for our present work here, I do not take a close look at this difference, but I really try to integrate the different types of energy. Of course, in everyday mobility, not only the question about what ultimately limits locomotion is of relevance. Like, it's not only reaching the destination. Of course, people will not use their electric vehicle until there's no energy left in the battery, and then they just leave their electric vehicle and complete the rest of the route on foot. It's not this alone. So maybe reaching the destination is maybe the major goal of mobility, but there's more. Everyday mobility also demands further considerations regarding mobility, like time, costs, comfort, and others. And these in turn are related to different vehicular tools and energy expenditures. Like, we cannot carry a lot of luggage on bike, but we can in an electric car. So mobility is diverse and pursues different objectives. And now I come to my main point. The main question here is, how can we optimally achieve our mobility needs with the available vehicle tools and with efficient human and external energy use? Important for the human-machine interaction here is a high controllability of the limiting and relevant energy resources. And all of the energy resources, not only one form of energy, so that users are empowered and capable to control the energy flows according to their will to achieve their needs. So external energy should be as directly perceivable and understandable as maybe one's own human energy is. Maybe that's not the case, but I assume this at this point. So this whole point is understood as an augmentation of the own human energy resources, and this is what we call today augmented energy for locomotion. Like, the vehicular tools help us to augment our human energy capacities with external energy. And when we talk about understanding and comprehension of energy dynamics and energy flows, then we mean the late concept of energy dynamics awareness. This is a concept that we introduced last year as a possible concept to moderate the efficient use of energy, so like a requirement for the efficient use of energy. This concept is deduced from situation awareness and describes a requirement for correct and energy efficient behavior. And that's first to comprehend the energy situations, to perceive and the relevant energy flows. So what is used for what and how much, and secondly, to be capable to control the energy flows. And we postulate that energy dynamics awareness is a key factor in the optimal energy related human and machine interaction, and that energy dynamics awareness can also help humans understand the augmented energy for locomotion. So we wanted to give this idea a first empirical try. So we conducted an empirical survey to get an idea if this concept of augmented energy for locomotion is applicable. And in the study, our research question was if we can measure a concept of energy dynamics awareness in all types of energy and maybe compare them and see where the differences are. So we took these 5 forms that I presented before of locomotion, and we built up a scenario. So the participants had to imagine they had to go 3.7 kilometers from the inner city of Lübeck to the university and had unlimited access to all those 5 modes of transport. And then we presented all the 5 forms of locomotion in a randomized order and told them, so imagine you're using this vehicle, and then after the presentation each form of locomotion was followed with 3 adapted versions of the energy dynamics awareness scale that we presented together with the concept last year. And this is basically so the EDA scale is basically assessing a subjective rating of energy dynamics awareness. So how capable do I feel to understand with which actions I can influence the energy consumption and how I can understand the energy flows. Yeah, for all 5 modes of locomotion, we asked 3 times the EDA scale for each type of energy. But for external energy, only in those cases where external energy is explicitly used, like in e-scooters, electric buses, and electric cars, we ask it. So not for walking and riding a bike. This would be too confusing. And these are the descriptive results. So for most, it becomes obvious that the awareness for muscular energy in riding a bike and walking is the highest. So in order to see if the energy dynamics awareness for different types of energy or different forms of locomotion is different, we performed 2 repeated measures ANOVA. In the first one, we include all forms of locomotion, but only the 2 types of energy, muscular and cognitive energy, that appeared in all forms of locomotion. And here we see a large effect size for the main effect form of locomotion, a medium effect for the type of energy, and also a large effect for the interaction effect. And post hoc tests revealed significant differences between the energy dynamics awareness in riding a bicycle and walking to all the other forms of locomotion. And also the awareness for muscular energy was significantly higher than for cognitive energy in all forms of locomotion. In the second repeated measures ANOVA, we included all types of energy, but only for the 3 forms of locomotion that had all 3 types of energy. And here the main effect showed that the awareness for muscular energy was significantly lower than for cognitive and external energy. In the first model, it was the other way around. The muscular energy awareness was higher. So to sum up, we can say that there are significant differences of the energy awareness of riding a bicycle and walking to the other forms of locomotion. Also, in an electric car, the awareness for external energy is significantly the highest, and for muscular energy, the lowest. That the highest score for energy dynamics awareness can be found in muscular energy while walking and riding a bicycle. This might lead towards the assumption that whenever external resources are traded for muscular energy, the awareness of those energy flows is reduced. And also these forms of locomotion that use external energy are more artificial and therefore raise the distance from us to our natural types of energy. But at this point, it's not valid to draw strong conclusions about the consequences of this observation. But this is a first empirical attempt, and it might be inspiring for further studies. We hope so. This might be especially useful for work settings where both types of energy are indeed scarce and relevant, like maybe in aerospace settings. And this perspective might be a novel approach in designing feedback systems for external energy, like in electric cars. Because what makes muscular energy so well understood that we can use it maybe for a user energy interaction with external energy. Yeah, I hope I was able to inspire a bit with this explorative concept, and yeah, thank you for your attention. Feel free to take a look at our blog or YouTube channel, as Murad also said before, and now I'm looking forward to your questions. Thank you very much.